Neural data compression, losslessly reducing bits with deep learning, prediction of NNCP and TRACE models. Data compression means encoding into less bits, encoding a message into less bits. Lossless means that we are not losing any information from the message during the compression. And trade-off, and basically data compression usually means that we are not losing any information. Trade-off, what we are doing during compression is we are making some sort of trade-off. We are reducing the message size for some computation and memory. So what we are doing is that we are trading off communication throughput and computation and memory. So this is the speed dimension of throughput that I mentioned in the previous post. And what does it mean? That sometimes we can even calculate fast enough the compression such that the message passes through our link and exact link speed, and by basically compressing we are increasing the bandwidth. Sometimes we need to store on some small disk for long periods of time, and we are increasing the throughput to the future of the stored message to the future. We can only compress if some symbols are more likely than others. Basically, if the current message representation is not optimal. And so the better we can predict the next symbol, the lower cross-entropy we achieve and higher compression we achieve. And that's where it is related to machine learning. If we have some kind of model which can predict very well the next symbol and achieves very low cross-entropy, close to the true entropy of the message, we can achieve high compression. Hi, so I am happy to see you again. So this was introduction to this post that I will continue on in a second. You can subscribe to my blog by mail. You can follow me on Twitter, YouTube, LinkedIn, Facebook, or RSS. Yes, and I have this blog post on my webpage, waclawkosar.com. And you can go through the blog post. There are lots of links. Recently, I did this big post on pathways language model video here, and there are lots of links. For example, I have this post on transformer. I have a post on cross-entropy, feed-forward layer, and so on. So let's get back to the post. You can subscribe there in YouTube as well if you find this interesting and share it with others. So first I would like to give some introduction to basic compression. For example, Morse code uses a compression. The compression is called Huffman coding. It's basically takes 26 characters of English alphabet and compresses them into dots and dashes. It does not compress white space. So basically there is, the space is not compressed. Each character is mapped to a sequence of dots and dashes, and more frequent characters are mapped to fewer dots and dashes. The principle is very simple. We can represent it by a tree, so we start here. So we may not transmit anything, and then it becomes a space. If we transmit a dot, we will transmit a character E. If we translate dot and dash, so that's double size of the message, we will transmit A. And this is a very simple principle. We can sort of remember, store this table, this encoding table, and the compression can be performed by human real time. So this is one of the compression algorithms. Another compression algorithm is very famous, Gzip. It's used in HTTP. It uses the deflate compression format, and this one uses, apart from Huffman coding, it uses this additional trick called LZ77. So basically it's two-layer First, we do this LZ77, which removes duplicate strings or tries to remove duplicate strings, and then we do Huffman coding, which reduces bytes into a couple of bits based on their frequency. And in this case, the frequencies are not static, but they are analyzed during the compression. So again, we have a sliding window of 32k bytes that is used to detect duplicate strings. Duplicate strings are then referenced back. So we find some duplicate string. Instead, we replace it with a reference to the stream and the length of the duplicate string. And we then transmit this along with the alphabet symbols. Once we do this, we can do second layer, the Huffman coding, and the Huffman coding based on the frequencies then encodes, creates the tree. The tree is stored with the data, and it compresses the message into less bits. For example, maybe this B would be compressed into 0, this L would be compressed into 0 and 1, similar as with the dots and dashes. What is interesting here is that we have here the back reference, that those are also symbols. So this L equals 3 means that 3 steps back, D equals 1 is a duplicate of length 3. So these would be also symbols, and Huffman coding would encode them into something. From time to time, these coding trees needs to be refreshed. Okay, arithmetic coding versus Huffman coding. Arithmetic coding can do better than Huffman coding. Why? Because what we do during this, as I mentioned, we are trying to reduce cross-entropy. And to reduce cross-entropy, we need to make the message size as close as possible to the optimal message size, which is not just we are sort of allocating these message sizes for each symbol between each other, and there is some optimal distribution of the sizes of the symbols based on their probabilities. So if we have a simple probability of Q, which then we are trying to achieve length of log 2 of Q minus, and that's what arithmetic coding can do, while Huffman coding does not, because Huffman coding always it has this 3 character that it always doubles, so we can see that it's not fitting any exact probability. It always uses this 3. It always sort of doubles from top down. And so how does this work? So this arithmetic coding takes an interval between 0 and 1, and it splits this interval into, you can see it here, and it splits this interval into the subintervals such that their size approximately matches the probabilities of the symbols. Then it represents those intervals in binary format, and it uses just enough bits that anything so that we have this prefix in binary point representation, such that we can then append anything after the symbol, and we will never escape from the interval. So, for example, if we have a symbol ABC, and so that's what we have here, then the first interval for AB will be 0 to 0.1. Yeah, and that's so only this. We only need to transmit this 1 0 here, because anything we append after the 0, any binary point digits, we will never escape from here, from this interval to this interval, to B, to the interval of B. Yeah, so only one bit code is needed to encode A. Does it make sense? Yes, because these others are twice less likely, and so they require 2 bits because they need to such that this 0.1 to make sure that it will not achieve by appending any bits after this, we will never spill into the other interval. We can actually we can only append anything, so it's two bits. We cannot just have 1 bit, we would be spilling. Okay, so this is how arithmetic encoding works. The lengths are then minus log q, which is what we want. That's something that Huffman encoding does not do. It's slightly slower, but it improves compression. And again, we are making a trade-off here. How exactly? How exactly does this work? How does it relate to cross-entropy? How compression, entropy, and cross-entropy are related? So if there is some true next probability given previous symbols of the next symbol, we never know this. If we knew this, we basically would not need to communicate. Yeah, in presence of perfect knowledge on both sides, there's no need to communicate. We only need to communicate new things, and so we will never know this true probability. And even if we know the true knowledge, then and we just want to hear what the others wants to say about that knowledge, we still don't know what part it's going to talk about. And so because we don't have the perfect knowledge is not shared, we don't really know what is the probability of the next symbol. We can only guess, but sometimes we can guess pretty well. For example, language models can pretty well guess the next word given the previous words. And arithmetic coding encodes into this logarithm of q, so a logarithm of this q probability of the next symbol probability. And so our average compressed message length is then cross-entropy, because we multiply the probability for the symbol with the length, and voila, we get cross-entropy. And but what is the optimal? So you probably know from the information theory that the optimal length, the optimal allocation, is with this true probability. We don't know this true probability, but we know this is the optimum. If actually all the probabilities would be equal, then we cannot improve on this. All symbols need to be equal size to get to the optimum entropy, so we cannot improve with compression. So this is intuition and how it relates. So if we can predict net symbol, how does it again look? How does it relates to machine learning? So so the Huffman coding predicts next symbol by basically using basic statistics. So it knows symbol frequency, and it's a sort of next symbol will be according to this statistic. Yeah, it will be based on what we saw. We will still stay with the same probabilities. So it has this static tree. But we can trade more memory and computation with more complex modeling. For example, you can do some language modeling with transformers, for example. And what we do during the compression, we can even train on the data as we compress them. And then maybe we don't even need to always transmit the model, because the model is deterministically updated. That's something that's not done in Gzip. Actually in Gzip we need to store the tables as part of the message. Okay, so what we what we do here in this visualization. So we have this BL question mark. Model takes the first part, so the first part, and for example GPT, right, it can predict the next symbol pretty well. It knows very well the distribution, what it can be. It's not never 100% sure what will be next. That's not deterministic, but it will with high probability predict that A is the next symbol. If we can do this, we can compress, because we achieve low cross-entropy, and this is going to be pretty good. So what are the common benchmarks in this area? So for example, ENVIC8 and ENVIC9 metric is bits per byte. But be aware, this bits per byte metric is not comparable with language modeling results. Firstly, the data compression usually is tried to be generic for any kind of data set, so it does not train somehow pre-train on just the Wikipedia or something. As well, if the benchmark in this case of the compression is different, it compresses the entire Wikipedia, not just some test set. And sometimes there are additional overhead. Maybe we need to store something extra in the message, and that increases the bits per byte. This dataset is used in both contexts of language modeling and data compression. Okay, so the two models that I'm aware of is NNCP, lossless data compression with neural networks. It uses LSTM to predict next byte. The model does not need to be stored in the output. We just need to make sure that we initialize the same, and then we deterministically can derive during the decompression what the model is. Basically, we regularly retrain the model deterministically, and the model tries to adapt to tries to predict the probabilities as it compresses. It is unfortunately 10,000 times slower than Gzip for twice less bits per byte. So the trade-off is not very useful. You can imagine that it's probably much cheaper just to buy twice bigger disk. And okay, so let's continue. Another model is this TRACE. It's faster than NNCP, so some around 3 times speed up is 1-layer transformer. It's still 1,000 times slower than Gzip. Still around it's competitive with the previous model, and so it's still twice more compression, twice smaller output, but yeah, it's not a game changer. Vocabulary, as you could imagine, is 256, so we predict sort of next byte. And actually, let me go to my real website, not the local. Yeah, okay, so so this is my website. Yeah, and so 256, and what it does extra thing that it concatenates 4 consecutive embeddings to this reduces the length of the sequence, and also it gets more similar to what we do in language modeling, that usually the token size is 4 characters. So 1 word is approximately 4 characters. And they do some optimization that they don't need to return as often. They monitor how well the model predicts, and then if it predicts still well, it doesn't do backward passes. And again, the costs for this are high. You need to use, for example, during the measurement of below, they use the GPU. So on embedded devices, this is probably oftentimes not practical. So deep neural networks for lossless compressions. For now, it seems to me that this is unpractical. Maybe there are some use cases. Let me know if you know about some. I think there's just the costs are high and the compression improvement is not that impressive. Maybe some lossy compression of images or video, especially with the video chats. Maybe that would make sense because during the video call, your face, your head is not going to change so much. You're only transmitting the expressions and maybe movement of the head, and so this is it. No, I don't think it's that practical. You can read this paper if you would like to know more about this. Okay, so as I mentioned, I have this website www.vaclavkosar.com, and yes, you can subscribe. You can subscribe there by mail. You can subscribe on Twitter, YouTube, LinkedIn, Facebook, RSS. And yeah, link will be in the YouTube video as well. Okay, thank you very much and see you in the future.